I was kind of messing up my whole career because we were going to solve all the security stuff. This is the mid-90s. We were going to solve all the security stuff, and really, I wanted to focus on networks and not security. So anyway, here we are years later, and one of the things that I'm interested in this topic is that sometimes we overestimate the security flaws or problems or impacts in new technology, but most of the time what we do is we underestimate it. And what I found really interesting in AI and ML is because there's so much weird magic fairy dust about what it is and what it means, that there's a lot of discussion on both ends. There's a lot of, and that's my dog shaking her collar, if you heard that. There's a lot of it's nobody's attacking AI and ML, and it's too new. Yeah, I hear that a lot, and that I shouldn't even be talking about it because it's basically nonsense. And I also, on the other side, have seen people that are actually already feeling impacts. And if you want to think about an impact of AI and ML that's very real and tangible, just think about the Zestimate. Right, the company Zillow, and I don't mean to call them out. I love them as a company, but it's a real world example. Zillow went into the iBuy. They had a business line where they were buying and flipping houses, and in order for that to be successful, they needed to buy the house at a good price, be able to estimate the cost of repairing it or making it more appealing to a buyer, and then flipping it for a profit. And it turned out that the Zestimate was a little bit over that algorithm that they were using was too generous, and that the actual value of the houses was not quite as high as it appeared, and they were not making profit on that business. So there's an example sometimes, and that's an unintentional failure mode. So sometimes with AI and ML, it doesn't have to be that an attacker's getting in there. It's just how we use these systems and what we're doing with them, how we're building them, and how resilient they are. So I'll start off with explaining a little bit about why AI and ML are different for us in security. We're all security practitioners. We've been doing this for a long time. It's our love, it's our life. But this is a little bit of a curveball. And I know I had to do some pretty deep research and educating myself to understand some of the differences, despite all the time that I've spent in IT. Then discuss both intentional, which is targeted attacks, and unintentional failure modes that can occur. And then we'll wrap with a little bit of how to threat model your systems for resilience. So first of all, what's really different? One of the biggest things I think that's occurring is our trust. Because we tend to trust computers. And I don't just mean if you've got some crazy thing going on in your social feed, you're like, that's just wacky. I mean, when you ask the computer to do something that you expect it to be good at, do you question it? And let me give you a specific example on that. If I give you two 10-digit numbers and I say, multiply these together, you're probably going to pull up a calculator, right? Do you then go, I cannot trust that system to have multiplied that properly? Then you take out your sheet of paper and you go and you do the multiplication longhand. How many people do that? Probably almost not. I don't know if anybody raised their hand, but probably most of us don't, right? In fact, it's very, very rare. It's almost to the other side. How often do you hear somebody say, I can't do that kind of math in my head. I need a computer or calculator to do it for me. So we trust systems pretty highly on things like multiplication, on finite math. But we're starting to use AI and ML in places where when we trust them, the impacts are going to be really great if they're not accurate. And it's harder to be accurate on these kinds of things that we're using AI and ML for to identify lack of accuracy than it is with calculations. So calculations, we did have that floating point error years and years ago, if you remember, where the hardware with Excel was actually not calculating properly because of a floating point error. It was discovered, but it did actually create some cascading impact. Now think about the impact of if your doctor says you have cancer when you really don't, because that system was not, if you're the robo-advisor that's managing your retirement investments has a mistake, right? So that the trust that we put in there and then the impacts of what can go wrong are really a little bit different than things that we've seen. Early on in IT, I think I would say that the impact, now that we look at, things like NATO having cyber as another dimension of war, we're starting to see some very serious impacts of when we can't get, when ransomware ties up supply chains, for example. But AI and ML intersecting into all of this can be some really big impacts. Another difference that's going on is that the big data tsunami has gotten even bigger when it comes to AI and ML, because machine learning needs data to learn. That's what it reasons over. That's how it learns. So the more data that we're talking about, then the more potential data for risk. If you've ever done software testing, you may know that a lot of companies use, they use dummy data when they're trying to test for something going into production, a new app. And then when you're doing an assessment or audit or security review, you realize that they were supposed to use dummy data and they used real data. And you say, why did you use real data? And they said, because the dummy data wasn't giving me the information back I have. So think of that kind of on steroids, right? We need so much data for ML. How do we make sure it's being used properly? It's not poisoned, it's not impacted. The visibility of AI and ML is also a really big consideration, because we don't always know that we're using it. When I was talking about this estimate, right, that's an example of, when you're looking at this estimate of your house, do you think that algorithm is nuts or whatever? We don't always know that it's embedded. Sometimes when you're talking to a chat online, for example, a chat bot, that could actually be a bot and not a person. It comes up with a picture of a person, but their face. But how do you know? On the internet, nobody knows you're a dog, right? Sometimes we are actually embedding AI and ML into systems where it's not clear that it's there. And then the last big piece of this is that for everybody who's here listening, we're all deep security experts, but are we data scientists? Are we AI and ML? And I know that I am still in the learning curve on AI and ML. There's a lot for us to learn. We don't have a lot of experts out in the field yet who feel really comfortable with understanding the impacts, the failure modes. So that means that we're constantly hearing about how there's no unemployment in security. Well, wow, when we look at what's going on with data security science and data scientists, we need a lot of experts to start focusing, security-minded experts, resilience experts to focus in AI and ML. So we've got all of this converging to create an actual real problem. I'm not trying to scare anybody. I just think this is an important thing for us to discuss as a community so we can address it now. And they're going to be talking about two different main kinds of failure modes, both intentional and unintentional. And the intentional is it's an adversary. Some kind of an attacker has tried on purpose to impact our systems. And I'd like to call out that there's a document, a really wonderful analytic document that a former colleague of mine, Ram Shankar at Microsoft, who's also known as the data cowboy, if you've ever seen him speak. And he's absolutely wonderful. He went to Harvard from Microsoft. He went over took a sabbatical and worked with some researchers at Harvard, and they put together a fantastic analysis of all of the research out there up to the point when they wrote on what kinds of failure modes occurred in AI and ML, and created this wonderful distilled document, which I used as a foundation. So I've got it referenced here. It's referenced out throughout this talk. And if you have an opportunity to go take a look at it afterwards, it's a great doc. They also have one on threat modeling. So it's both really, really informative pieces of information. So what kinds of intentional failures are there? Here's a big list. I'm not going to read through it because what I'm going to do is I'm going to talk you through these different failures, but I got little breadcrumbs. So as we go through, the images will link up to what you're seeing. And then unintentional failures. What happens on accident? Nobody actually tried to bring the system down. But if we didn't test or build the system properly, as you know, things can fail. When you start up an app on your phone and it doesn't work quite right, and it crashes, do you think an attacker's attacking it? They could be. Or do you think, probably just wasn't tested that well and it's a buggy or unstable version, right? And so that's what the unintentional failures are. It's just design flaws and other failures of testing and other things that were not intended to make the systems fail, but they did. So on the intentional side, the first one that you've probably already heard this is perturbation attacks, because this is one of the ones that is talked about the most commonly. And this is about adding noise into an image. And the thing about AI and ML, and especially ML, machine learning image classifiers and computer vision in general, is that sometimes that perturbation, that noise, that extra fuzz in the signal, it's not visible to us at all. It's like back in the day when the steganography attacks were happening, we couldn't see in the image that there was a stego attack in there. This noise that happens in AI and ML and perturbation attacks, we also don't necessarily, we're not able to see it. So there's an example here from Goodfellow, and it's a panda, and the classifiers had a 57% confidence that it was a panda. So pretty sure it was a panda, but not super sure. But then there was the interference was introduced, and it's still, like, to us, it looks like a panda to me. I don't know about you guys, looks just like a panda to me. But now the classifier has decided has classified this as a gibbon, which is not a panda. And interestingly, it's even more confident. So if you were saying, well, think back to that calculator with the 2 big digits, and could you imagine if you get this number from your calculator and it says, I'm 99% sure that's right. First of all, that feels a little bit odd because you want it to be 100% right. But then also, if it is 99, you're like, that sounds pretty good. You might think that 57% it feels less right to you, but it turns out in this case, because of the perturbation, the 57% was actually closer in accuracy than when it was perturbed. And what happens in AI and ML if we've got perturbation? Well, let's go back to that radiograph. You go to the doctor takes an x-ray of your chest and says, this is a tumor, or it's not a tumor. Or this is benign, or it's not benign. This looks like a problem, or it isn't. Well, what if there was perturbation or noise in that image that led the classifier that the doctor might be using? Because a lot of doctors are trying to use ML, image classification, to be even more accurate and to be able to say that is a problem with that tumor or it's not. So they're saying, let's take the human out of it, let's let a machine do it. But the machine, as we can see, is not always going to be right, especially if there's been an intentional attempt to perturb the image. Another example could be in text translation. If there's a lot of noise, perturbation, then you could have a change in the word's meaning, or it could be that important data is dropped, changing what the person's saying. Now, perturbation is not that easy to do because you have to do it for each image. So some people have said, well, it's too hard an attack to actually launch. So researchers said, well, how about universal perturbation attacks? So instead of just having unique perturbations or noise per image, what if we were to introduce this universal perturbation, this universal noise, and see, is that also going to work? And it did. As you can see in this image, we've got here, I think we have a joystick becomes a chihuahua, for example. So when just having this one little bit of perturbation, but putting into all the images was actually caused misclassification throughout. Next part of intentional failure that can occur is if an attacker on purpose attempts to poison the data. And the data, because this is what the systems are using to either make decisions from or to classify from. If we poison the data, then the data that they learn from is going to impact the accuracy of their outcomes. And an example of this would be Tay. And Tay was a Twitter bot that the Microsoft natural language team put out onto the internet. What they wanted to do was they said, let's get some natural language learning. What's a good place? There's a whole lot of natural language going on. Well, it's out of Twitter. So they created this bot. It was very, very clear that Tay was not a human being. There was no intent to deceive. It was just to see, how Tay would react to this natural language, how Tay could learn more quickly while engaging in all these conversations on Twitter. Well, what happened in the example of Tay specifically is that within 24 hours, a whole bunch of people figured out that they could poison Tay with the data by rather than having nice conversations with Tay, who was all sort of the bot was sort of super happy, kind of a tween when the bot got onto Twitter. Said, look, let's poison the data that we're sending into Tay instead of having be normal conversations. It was really horrible, racist stuff. So in less than 24 hours, Tay, who was now repeating back a lot of the data that Tay was ingesting and saying it in response and trying to have communications, was saying really horrible, terrible, racist stuff because the past conversations were influencing the future output of that bot. So they had figured out how to poison the data in the sense that they got Tay to say really awful things. So Microsoft took it down, took the bot down because of that. So you could also do this sort of in an indiscriminate way by you could just feed so much garbagey data, that classic garbage in, garbage out. You could feed so much garbage into a model that if it's learning in production, that it becomes kind of worthless because you've created at some level a bunch of noise again, but it's by noise by feeding in poison data. And then it becomes a little bit of like a denial of service because again, if it's not accurate, it's not going to be very useful to us or fairly accurate. Another attack is reprogramming neural networks. And this is actually sending unintended queries to the model and trying to get the model to learn to do something that it wasn't initially intended to do. So vision classification is an example of, if you're saying vision classification for radiograph, or what if you could take that model and you say, can I get you to classify other 2D images, for example, crosswalks and mountains and traffic lights. And in that case, then how would an attacker misuse that? They could do it to pass the image classifier. You could probably guess what I was saying because you got captured, right? Where I was going with mountains and crosswalks and traffic lights, right? We all have to do that. But in this case, using that neural net to be able to complete things like CAPTCHAs and then appear to be a human, and then that would override all the security or the at least the availability that you're protecting with the CAPTCHA, because CAPTCHA is usually to stop bots from doing things like buying a bunch of tickets or creating a bunch of accounts. Whatever it is that you had a CAPTCHA that you were trying to say, I need a human there, not a bot. Now you've got a bot finishing the CAPTCHA. 3D adversarial objects is another area where researchers have seen that there can be some big failures in AI and ML where an attacker could do an intentional kind of attack. And this one is around, I have been talking about 2D image classifiers, but you can also do 3D image classification. And if you've used some of the facial recognition, there's some elements of trying to figure out 3D, if you're there in 3D. So if you just hold up a picture to most facial recognition nowadays, it's not going to work. It's going to recognize that that's a flat 2D object. So we're using classification and image to be able to put in context and space 3D objects. But how good are our classifiers when we go to 3D? Because now they have more angles that they can look at, but there are also different ways to trip them up in the physical world. And sometimes these are referred to as ML optical illusions because it's an optical illusion for the machine learning system, which could have pretty big impact. In this one, what the researchers did was they printed out a 3D model of a turtle. But they did it in such a way that when it was presented to Google's V3 image classifier, it was determined to be a rifle at every angle. So that's worrisome. The turtle to rifle, that could be a problem if it's in your luggage. For example, what if somebody gives you a gift when you're leaving a place, they give you a gift to take onto the plane and it's a turtle, you get stopped, and there's some scanning, the scanning thinks it's a rifle. That could be a problem. The other thing, although TSA is going to open up your bag and go, it's a turtle, right? But it could make you late if you were late for your plane. In the reverse is where it could get really concerning if someone could print a rifle that's scanned out by one of these scanners as a turtle, then that could have a lot more serious implications, as you can imagine. Another thing would be like a sign to an autonomous vehicle where it's a stop sign to us, but to the autonomous vehicle, it's a 65 mile per hour speed sign. So instead of stopping, the car speeds up, and so I can go 65 miles per hour. Supply chain attacks, and a lot of us are dealing with yet another software supply chain attack, right? With a software dependency with a Log4j going on. Supply chain attacks are when the attacker gets into the supply chain and somehow poisons or otherwise interrupts the performance. And here's an example of with model zoos. Model zoos are pre-trained models that scientists use to be able to do testing, to do research. It's great. I mean, pre-trained models are very, very functional and very useful and are advancing the state of the practice. And there's a really famous one, GPT-3, which is used for language. And this is a cool, it's pre-trained on language, and you can go to it and say things like, give me a cookie recipe, and it'll come out with a cookie recipe. Or I love a COVID poem, and I want this COVID poem to mention my dog, and it would create a COVID poem about your dog. So it produces this really nice human-like text. It would be very, very costly for companies to build and train a model like this themselves. So it's great that there are pre-trained models out there for research purposes. So model zoos are good. Pre-trained models are for good. Where the risk or the attack point comes in is, sure, if somebody has got a pre-trained model it's been poisoned, it's got malcode in it, for example, it's been otherwise tampered with, so that you use this model and the outcome is inaccurate or harmful or misleading. In model inversion, this is when the access to the model is able to allow the attacker to uncover private information from the data set. Oops, sorry. That was not a bot that did that. That was me who just put my finger on the mouse. But with model inversion, they uncover this information. Very often when they're using machine learning as a service, that's a way to get access to models. So if you're saying, well, how does somebody get access to the model? If you're using machine learning as a service, there's an API. People can write to it, they can get into this model, and it's again often used for research to allow more people to have access to a model, especially if it's a pre-trained one, or just to a model in general. It's going to do classification. But if data can be extracted from that model, that's a privacy issue. And in this piece of research from CMU, a facial recognition system, just by querying the model, just using a name, they were able to pull back the face of people that had been in the training data set. So, in this particular case, people probably submitted their faces. Our faces are public, but it can have bigger impacts when you start looking at more private data, when we're looking at models that are being used in healthcare environments and things like that. Model inference, which is again determining part of the training set. In this piece, hospital discharge data was inferred using queries to the system. So just by understanding a little bit about what that model was processing, the researchers in an emulated attack were able to just send in some information to a large database that was using actual public records in Texas in a hospital system, and be able to figure out what the main surgery or reason that person had gone to the hospital and why they'd been discharged. So we're starting to get we're going from faces now to some medical data. So you can see that as we use these systems for more and more private information, as we have access to it, we may think, well, that training data isn't going to be available. With model inference, and model, there may be ways to extract some of that data. So we want to be able to be really careful with that. And then with model stealing specifically, this one is about an attacker being able to figure out what your secret sauce is in that model. As a lot of companies, and we've heard it all from the security companies, we go to RSA and the whole floor is like, our ML is the best ML, it's perfect, it's going to find all your attackers. Wouldn't that be great? But companies are spending a lot of money developing and training multiple models in order to be able to provide different services like security analysis. that's an investment from the company, and it's also a competitive advantage. If an attacker can uncover the secret sauce in your model, then what they can do is they can go emulate it. So competitively, that means that whatever you thought was your big, look at our wonderful ML model, look at our ML, it's much better than others. Well, now your competitor has that. So if you're like a credit company and you have an ML model that does really good risk analysis on whether somebody should get a line of credit or not, right? Your competitor, then they don't have to spend all that time or money. They just have that model because they stole it. So that's one thing, is competitive. The other thing about the stealing the models is that attackers, once they steal the model and understand how it works, guess what they can do? They can sit there in private, because now they can replicate your model. They can sit there in private and see how, because they're not interacting with your model anymore, they're interacting with that replicated version. See if there are ways that they can get around that model, poison the model, or otherwise damage the model's accuracy. So they could bring, they could cause damage and impact to your company that way. Basically plan new attacks because they've got your model to test on. And then our friends, backdoors and existing exploits. ML and AI work in the world just like all the other software we deploy. If you've got a hardware error on your supply chain error on your laptop, if you've got a buffer overflow within the software and the operating system, that's all going to impact the accuracy of your AI and ML. So an attacker may not have to actually attack your model itself, your algorithm itself. Maybe that they just have to take the operating system or the hardware platform, or maybe the VM going up a little bit higher, and create a flaw around that and create damage that way and actually cause a failure that way. So they can also, in context, right? Because you have to have the whole chain, as we know, has to work accurately. The other thing is backdoors. So attackers are looking at backdoor triggers, just like you get a cheat code, in your favorite games, looking at backdoor triggers that a developer may have left in there so that they could test some kind of cool or interesting or unique functionality, or so that they could go in and do something, trigger something within the model, looking at putting in backdoors to the system itself to trigger. And there was an interesting set of research around like a sticker on a stop sign doing just that, creating a trigger for the autonomous driving car. So those are the intentional attacks. Now I'm going to talk a little bit about unintentional attacks, and these are failures of design. And the first one is reward hacking. And this one, the reason that you got a picture of the Seine in Paris here is that my favorite version of reward hacking actually started with a dog, not with AI and ML, but it was a dog that years ago, it heard a child crying in the water as it was, it was on the Seine. And so the dog jumped in and it saved the child and it brought the child to shore, and it got so much love and attention. And it was such a big story. This was about 100 years ago. Such a big story. It was even covered over here in the US in the New York Times. And the dog got beefsteaks and everything. And then a couple days later, the same thing happened. And again, the citizens were like, this dog, thank goodness he's here. He's saving our children from drowning. And the dog got a lot of attention and extra food and everything. And then it started happening just like almost every day. And the locals were like, I don't know about that. And so they started watching the dog more carefully. And it turned out that we don't know if the first couple times this has happened, but as it was happening frequently, the dog, and I suspect the dog figured out that it was getting a lot of rewards. So it started like bumping kids into the water so that it could go save the children. And that's classic reward hacking. And believe it or not, but models and evolutionary algorithms and AI, that they can reward hack too, especially if you're doing the reinforcement learning with them. They are going to do the equivalent of knocking the dog into the water. So a classic example was that there was an AI gaming system, and the sim parents were looking for energy ups, and the developers hadn't thought about I don't know why, but everything had sort of an energy value, and the children actually of the sim parents had energy values. So nobody had realized this or thought about it until as the game was trying to learn how to be really good at it, it had figured out that it could reward hack and eat the children and get extra power ups, which in a game, that's maybe not a big problem. But if you've got reward hacking in something, say like a physical system where you've got a robot that's supposed to do your cleaning, you got, the floor robot that's supposed to do cleaning. If it gets rewards for cleaning up more messes, then it could start creating the messes, just like that dog was knocking the kids into the river. So just looking there and understanding that as we design the systems, because sometimes if we don't think about what could go wrong, and we have to think about the threat models, the things like the sim parents eating their children. That was a surprise because it was not expected. And something that's related to this also with reinforcement learning is side effects. When the physical reality, the physical ecological environment creates something that isn't that wasn't planned for, that wasn't planned for within the rollout of the system. So let's go back to our robot. We got our cleaning robot, and the example I had before, it was trying to get the reward. So it might knock things over in order to get the reward because, now I have something to clean up, right? I get a reward. In the side effects, it's just looking for the shortest path to execute what it's supposed to do. So you give it a task. The task is go and clean up the spill. And it didn't make the spill, but it wants to go to the spill as quickly as possible. And if it doesn't understand the room, the 3D, the physical environment of the room, it could run into a table that's right in the middle of the room. And then, precious vase, for example, could get knocked over. And if it's running into children, think about what if we're on like a shop floor, a really busy shop floor, and we've tested our cleaning bot in an office building at night, and somebody deploys it out into a shop floor and it's very busy and maybe it's wet too. So, people are more likely to slip. Now that bot that was running around doing really well in the office building at night could actually be creating a lot of chaos and even injuries if it was on the shop floor. So also thinking about all these different environments. And I've given you just a couple of examples, but as we roll out AI and ML more and more, the testing, complete testing, and trying to threat model for all the different environments that we deploy in is going to become more and more important. And it's just sort of really about thinking about this early, because for the people that are saying, hey, AI and ML isn't here, or it's all, it's self-healing, it's going to fix itself. It's not. Distributional shifts, it's not unless we build it that way. This is when you test it in one environment, but it's used for another one. So back to the robot, if you train it to avoid obstacles, great. You say, let me map the room. But then what if you move the furniture in the room, for example? Or if you just introduce new data entirely and it shifts. So over time, data can shift. You could, if you're using for retail predictions, which a lot of companies now do, they're trying to figure out what people are going to buy in the next 3 months based on what they bought in the past. But if you were trying to figure out, they're going to buy pants or are they going to buy leggings, right? Because apparently a lot of us wanted to have much more comfortable soft pants when a lot of us started working from home. Well, what if there's like jeggings, right? Jeans and leggings. The model isn't going to know about the jeggings. It was trained on jeans and leggings, and jeggings now are all the rage. So you've got to shift. Can you retrain it? Yes, of course you can retrain it, but you have to know to do that and take the steps in order to do that. So if you've got ML, for example, helping you with like automation of compliance and privacy regulations change, you need to make sure that you're readdressing for the distributional shifts, because otherwise you're going to have out-of-date systems that aren't going to be accurate, and you could give you false sense of security. And then a really big one is incomplete testing. And common corruption is a great example here, out in vision with cars. So I've got this stop sign picture, and you look at that, that looks just like a stop sign to you and me, right? We can recognize that because humans are really good at context. It doesn't matter that it's not really red anymore, that it's got all this like crazing on it, all that, we get it. It's a stop sign. But for a computer vision system, the real world is really, really difficult. This is one of the reasons that autonomous driving has not progressed as fast as some of us had hoped, because it turns out that when it's a little bit dark outside, when there's glare from the sun, when it's too bright because there's glare from the sun, when there's snow, when there's rain, all of these things impact the computer vision's ability to parse what's being seen. It's hard for us to understand how hard that can be because we are so good at context. It's like the whole reason that Rosie the robot isn't here yet. I always use this example. We can pick up glasses so easily. I mean, think about this. This is a pretty heavy glass. You can probably see that it's a glass, right? And when it's full of liquid, it's got some serious heft. But my brain can instantly calculate just how much pressure to pick this up with when it's full, when it's half empty, when it's empty. Right? Your brain, all of our brains can do that, not just mine. But anyway, think about the amount of calculation and that goes into making that decision, and we do it without a thought. We're not throwing our water behind us, right? We're not sitting there going, I can't lift this, right? We do this, and if it was a paper cup, I could do it. If it was a ceramic cup, right? We forget how good we are at context. And that is, I think, a big problem with AI and ML, because we don't understand how much we need to give these systems. So testing them in very realistic environments. Another big one, underfitting and overfitting. Overfitting is when you kind of overtrain the system. So, and both of these lead to inaccurate outcomes. Overfitting is when you train it on a bunch of data that is very unique, and it's very good at predicting outcomes from that training data, but it's not good at creating predictions on new data. And it can happen because you haven't given it enough training data. It can also happen when you give it too many variables. So if you were trying to predict the weather, you could have variables like time of day, geolocation. But if you start doing things like number of cats in the neighborhood, that's probably not going to be a good indicator for weather. So that's when you get overfitting. Underfitting is when you just haven't trained it very well at all, and it's just not performing. So the predictions are not good. So both of these are result in inaccurate outcomes. Again, nobody attacked your system, but your system's not working as expected or as it should. Big one here, data bias. We get similar outcomes to poisoning, but in this sense of data bias, it was not intentional. So you throw off the weighting of the algorithm, and that then creates analytical errors. And one of the funniest ones was about hiring. And there was data bias in a hiring tool, and it started to favor people named Jared who had played lacrosse. So if you think data bias doesn't exist or can't happen unintentionally, it can. And that was a really interesting one. How does it happen? Some common types of bias that we've seen in AI and ML. One was on facial recognition. Facial recognition's tested from very large companies, Microsoft, IBM. The MIT Media Lab determined that they were misidentifying 35% of darker skinned females. So the facial recognition did really well with white males, not so well with darker skinned females. And that's partly sample bias. It was trained on a sample that it was good at, but it wasn't good with the non-sample. Exclusion bias is if we think something's not important, but it really is. So an example would be a retailer that is trying to figure out, they find out that only 3% of our buyers, or here's one, I saw it this morning in the New York Times, it's good. So you know how we've all heard about the Great Resignation? Well, when they exclude, it turned out, looking at the data, that of all the people that are quitting their jobs, 90% of them are over 55, and they're not quitting to go anywhere else, really. It's retirement. They've decided to early retire. So if once you exclude, in that case, excluding that group changed the analytics significantly, because now 10% was left. So exclusion is when you think a group doesn't matter and it matters a lot. So if you thought, well, the millennials don't matter so much in this Great Resignation, or you thought over 55 doesn't matter so much, they did. It turned out that they were 90% of what was contributing to that. So it's that lies, damn lies, and statistics kind of thing. This is math, and we need to make sure that we don't create bias in the math. And then association. ImageNet, this was an interesting one. In ImageNet, they were just a person who was at a bar, was just having a beer with friends, was labeled a lush. There was a person that was on a beach with sunglasses, and they were labeled a loser. So if you're starting to use image classification to try and understand, should I hire this person? If you've got misclassification like that, that can be really problematic. Another example would be, what if the model starts to think that men are doctors, but women can't be because it's associating men. So all different kinds of bias, we want to extract all of them. And we want to build really a resilient, strong AI and ML. And there are 3 key ways to do that with data hygiene, adversarial training, and controlling the access to the APIs. Your training data hygiene, core one here, eliminate that bias. That means, looking at the sample, making sure it's going to work for all, making sure it's going to work for everybody that uses it. Limit the integrity to the data, the training data, and then to the system in production. That'll be the API, because otherwise somebody might poison it, intentionally or unintentionally. And then also make sure that you've got enough data so that you can avoid that underfitting and overfitting. So training data hygiene. And here's a checklist. This is from that threat modeling document that I had recommended. But these are some things to check. If it was tampered with, what kind of warning would you have? Where's that data coming from? Is it from a source that you trust, or is it not? And if the outputs of your model are not accurate, how would you know? So start asking those kinds of questions. Adversarial training is it's one of the best defensive techniques. It's like creating immunity for your system. You're training it to be strong, almost homeopathically, training it to be resilient. And the way to do this is that you create adversarial examples that you then use as part of the training process, so that the system can get used to hearing noisy information, or get used to, and that would be both online, but then also offline in the real world, because we are using, and that's things like computer vision and autonomous cars, so that it can get trained for, if we train it for snow and wind and rain and really old stop signs, it's going to be stronger and more resilient. So some actions here to help with is, are you training with adversarial examples? What happens if somebody copies your model, for example? And how are you interacting? What would happen with PR backlash, for example, if there was inaccuracy from your model? If your model is used to tell people if they're sick or not, or your model is used to predict what your company should be investing in next, or how your company invests retirement money, for example, what's the feedback, or what's the impact on that? And then APIs. I talked about this with machine learning as a service, and how we have model zoos that are available. A lot of this, how are we interacting with them? We're interacting with them through APIs. So we need to really be very careful to extend whatever API protections and controls that we have in our normal development, that make sure that we're extending them both to our own AI and ML, and also to understand how our partners are using them and their programs, and that they've used it too. And we go back to the principle of least privilege, and need to know here, another key with the APIs is to hide the confidence scores. Don't have chatty APIs. That's one of the ways that the inference works. So you start to figure out what's going on within that model. So don't have chatty APIs. This is not anything new. I know if you've done defensive development before, but let's just extend it out to AI and ML too. And here's a checklist for that. Who's getting the training data? Have you scoped that down? And what are your third-party dependencies? Because knowing where your dependencies are, again, as we've all been dealing with in the past week, is really important, because a lot of I don't know how many of you were involved with people saying, we don't have any log4j. And it's like, well, you're using this product or this product or this product. And they're like, oh, we've got a lot of log4j we have to deal with. So our dependencies and access matters in AI and ML too. So hopefully we can get ahead of the next software supply chain problem. So with that, I want to thank you so much. I hope that this was, I'm trying to stop the sharing here, but it's not stopping. There we go. Thank you so much. And I hope that this was helpful. And I know you've got a break now. So thank you very much.
Actually, Diana, that was awesome. Thank you so much. We have some questions. You can read them, or I can help you out there. We have one from Brian Schultz. He had not thought of the trust issue with AI and ML. Right now, he doesn't trust many sources for truth. Yeah, clearly. As there are influencer bots, unfortunately. So, right, that if we start to distrust computers as they are programmed to lie to us, OS1s are not what they seem. For example, deep fakes have become so good. What a mess. How will we get back to the ground truth so we can, once again, trust systems?
Well, I really hope that there's going to be, at least with AI and ML, I hope that there's going to be a lot more focus on building resilience in, having ethical development of it, because it's not going to happen by magic. And and a lot of people kind of think like, oh, AI is just going to fix itself. It's going to be like that Finch robot in the Tom Hanks movie. It's got to be us. We've got to say that this matters to us. You've got to tell vendors that it matters. You've got to start implementing standards and taking this really seriously to make sure that we can build systems that are as accurate as possible. And when they're inaccurate, that we got an alert, we can address it. But yeah, thanks, Brian. And I agree. It can be a mess. Maybe it made the decision too quickly to try Panda Express. Okay. And neutrality. Well, of course, this is the $1 million question. And I have a whole talk on bias, and this is a deep, deep subject, but the high level answer is that human beings are always biased and we don't see our own bias, and that machine learning drifts towards bias. So this is going to have to be a combination of working together as you're designing, as you're figuring out which data sets to use. Have a team, get a lot of different viewpoints on it, and have people with different viewpoints, different backgrounds, different expertise, because it's very, very hard. We don't see our own bias. I don't see my bias. Don't see yours, probably, all of it. So so it's a really big one, but the main way is to get a lot of different eyes on it, have discussion about it, and be aware of it. I don't think we'll ever eliminate bias, but I think we can at least make things much more usable by all, and at least not automate really, really extreme bias.
Yeah, there's a lot of discussion, and a lot of companies are actually doing implicit bias training for their workforce.
Yeah.
And people who are very open-minded, very, very open and welcoming people, answered questions and then realized, and they were terribly embarrassed. I guess I have some implicit bias, but how can that be? And it's amazing how many people, we all have something that we're just not aware of.
We do.
But that group team approach that you were talking about, there have to be cultural, racial, ethnic mixes to make sure that different ways of looking at things are being addressed, and that bias hopefully I can cancel some of it out, right?
Yeah, at least we can do better than just getting a CV that's like, I only want guys named Jared who played lacrosse to be on my development team. Like
they're the best scorers,
yeah. Yeah.
Okay, I think we've gone through all the questions. It's great that you were here again, and love the topic. I want to thank you very much again. Appreciate it.